Good morning, everybody. Welcome to today's session. We are discussing the chapter metal clusters. Today we will have a third lecture. In the last class, I have explained you the tetranuclear metal carbonyl cluster structures. And I have explained relative stability of bridged and non-bridged structures of tri and tetra nuclear metal carbonyl clusters. Last class we have discussed this. So today we are going to have new topic said as Wed's rule. This is also termed as polyhedral skeletal electron pair theory. Skeletal electron pair theory. When it comes to Wed's rule, it defines the structural aspects of higher nuclear metal carbonyl clusters. Before Wed's rule, till the last class, we have discussed the structural aspects of trinuclear metal carbonyl cluster and tetranuclear metal carbonyl cluster, which comes under into low nuclear metal carbonyl clusters. So now we have to move on for high nuclear metal carbonyl clusters structures. So to explain the structural aspects of high nuclear metal carbonyl cluster, we are going to have Wed's rule, where here Wed's rule also called as polyhedral skeletal electron pair theory. Here we have to know what it means by polyhedral, right? You may not know what is polyhedral, so I will explain the polyhedral, what it actually means. When it comes to a polyhedral word, it has two terms. One is poly, another is hydral. Poly, it means, you know this, it means multi or more. It means multi or more. When it comes to an hydral or hydron, means trigonal phase. So in total, polyhedral nothing but multi-trigonal phase. So here the structures what we have in the high nuclear metal carbonyl clusters will be polytrigonal phase structures, right? So thus polytrigonal phase here we terms as polyhedral, and thus polytrigonal phase skeleton electron pair theory, which nothing but the polyhedron what we will have in the high nuclear metal carbonyl clusters will be defined with respect of skeletal electrons will be defined by skeletal electron, right? So here you know that what it means by skeleton. So the core structure defining things will be called as skeleton, right? So here, as we are started the discussion of metal clusters, we said that the core structure, the skeleton structure is depends upon the metal to metal bond rather than metal to ligand bond. As we defined the metal clusters, The metal clusters are the complexes where it having an multiple metal atoms with direct metal to metal bonds and substantial bonds, right? Where the substantial means the importance of metal to metal bonds, and said that the metal to metal bonds only defining the structures of the metal clusters. So here the skeletal electrons will be counted from the metal to metal bonds, right? So such metal to metal bond electrons defining polyhedral or multi trigonal phase structures will be there into the high nuclear metal carbonate clusters, right? And so when it come, we have to see that how does the polyhedrons, right? How does the polyhedrons will exist? To know the polyhedron structures, we have to know another term, that is vertex or vertices. Vertex or vertices, right? Vertex or vertices nothing but it is a corner site of structure. For in structure there will be corner sites, right? So thus corner sites will be termed scientifically, we will be have a term of vertex. Its plural will be vertices, right? So vertex, which means the corner site of the structure, right? So when the corner sites or vertices will be 3, the polyhedron structure will be trigonal face, will be trigonal face, right? Here the n means number of vertices, right? And when n is equal to 4, vertices number will be 4, then the structure, the polyhedron structure will be trigonal, sorry, tetrahedral. It will become tetrahedral, where the vertices will be 4, where the vertices will be 4. 4 vertices polyhedral is tetrahedral, 3 vertices polyhedral is trigonal, where 4 vertices polyhedral will be tetrahedral, right? Like that, when n is equal to 5, right, vertices number when it is 5, then the polyhedron will be trigonal bipyramidal, right? The structure will be like this. One vertices, second vertices, third one, fourth one, and fifth one, right? This is a trigonal bipyramidal. When it comes then vertices number 6, when vertices number is 6, then the polyhedron will be polyhedron will be octahedral, right? And the octahedral structure, you know that like that. There are 6 vertices will be there, right? So like that, there are multiple polyhedral structures we will see, right? So those polyhedral structures will be seen in high nuclear metal carbonyl clusters, right? These structures will be defined by skeletal electrons, right? So now we have to look into what it Wet's rule, how does it is, how we are going to have the polyhedral electron pairs number. With respect of that, we can define the skeletal polyhedron. So actually, as per the Wet's rule, all the metal clusters will have a building block unit. Will have building block unit, and this building block unit is M.Sc taken thrice. Tricarbonyl metal will be the building block unit, will exist in the metal clusters, right? So when that exists building block unit, each building block unit will be contribute 12 electrons. Thus building block units each will contribute 12 electrons, and thus 12 electron, how it contribute is, we know that the tricarbonyls, when it binds with metal, the carbonyl will donate a pair of electron from carbonyl to metal, and also it will be shares electron density from metal side, as the carbonyl is pi-acidic ligand, which means it can donate the pair of electron and acts as a ligand, and it also accepts the electron density from the metal, so it acts as a acid. So with that respect, carbonyl is pi-acidic ligand, right? So in that means it donates a pair of electron towards the metal and it accepts the electron density. Like that, in all three, they will donate pair of electrons and accept electron pairs, right? So we know that each bond will be formed with respect of 2 electrons, will have 2 electrons. So in one metal to carbonyl bond, there will be 4 electron density may exist. 4 electron density may exist, such that in building block unit of tricarbonyl metal, there are 3 bonds. So thus 3 bonds will be have each 4, which nothing but 12 electrons they have. The building block unit will be have 12 bonded electrons where they will counted, right? So like that, each building block unit will contribute 12 number of electrons, where the metal clusters will have multiple or n number building block units will be have. It has, right? Then therefore the electrons contribution will be 12n, will be said as 12n, and thus 12n said as termed as non-skeletal electron pairs, non-skeletal electrons. It will be said as non-skeletal electrons, right? So why they has to term as non-skeletal? As we already said that the skeletal of the metal clusters will be defined with respect of metal to metal bond rather than metal to ligand bonds, right? So here whatever the metal to ligand bond counts, they just the part of excess of the skeletal, right? The skeletal will be defined it with respect of metal to metal bond. So here the 12 electrons contribution is done by from metal to ligand. So they may not be comes under into skeletal, right? The bond may not be defined as the skeletal of the metal cluster. So far they termed as non-skeletal electrons, right? Whereas here the skeletal electrons counted as 2 into n plus 1, 2 into n plus 1, where n is equal to vertices, number of vertices numbers, right? Vertices number, right? So that is what the skeleton. So to have the from the for an metal cluster, by looking into a structure or by having the metal cluster formula, we can easily count the non-skeletal electrons, right? Whereas to have the skeletal electrons which defines the structure, we have to go for next, right? That can be drawn or collected from the total electron count, right? Where the total electron count is equal to number of, it is similar as 18 electron count. Total electron count can be similar as 18 electron count, where it is equal to total electron count equal to number of metals into valency electrons plus number of ligands into ligand donating electrons plus or minus oxidation state on coordination sphere, right? Plus or minus oxidation state. So this is will reflect the total electron count, and total electron count is defining the all the electrons which come into bonding, which contributing the bonds, and whereas the non-skeletal electrons are reflecting the metal to ligand bond electrons, right? Electrons pairs participating in the metal to ligand, whereas the skeletal electrons reflect the electrons which come under into metal to metal bonds. So we can say that the total electron count can be written as skeletal, additional product of skeletal and non-skeletal electrons. Skeletal electrons plus non-skeletal electrons. Isn't it? Whatever the bonds it comes in metal clusters, it may be from metal to ligand or metal to metal. Whereas the metal to ligand bonds reflecting number of electrons by non-skeletal electron. Metal to metal bonding electrons can be reflected by skeletal electron. Whereas the total electron count reflects all the electrons. So the total electron count can be written as the additional product of skeletal electrons plus non-skeletal electrons. From this count, we will be have the non-skeletal electron number, right? Isn't it? These, to count the total electron count, it is easy from the formula of the metal cluster, and whereas from the formula we can also count the non-skeletal electron. Having total electron count and non-skeletal electron number, we can easily count the skeletal electrons, right? So from the skeletal electron, we will be have the vertices number, right? Isn't it? Where the skeletal electron is equal to 2 into n plus 1, where n is vertices number. When we have the vertices number, we can define the polyhedron. The skeletal polyhedron can be defined. As such, we said that when vertices number is 3, the polyhedron will be trigonal. When vertices number is 4, it would be tetrahedral. when vertices number is 5, the polyhedron will be trigonal bipyramidal. When vertices number is 6, then the polyhedron will be octahedral. When vertices number is 7, it would be pentagonal bipyramidal. Like that, there will be multiple polyhedrons are there with respect of vertices number. And that's how we will be defining the, we will going to define the skeletal of the high nuclear metal carbonate cluster. So this is how the Wed's rule will be there. So this we will, when we go into an one particular example, we will be exactly know the how does we will have the structures of high nuclear metal carbonate clusters. Now we will going to do one of the examples. So here is the example. (15) carbonyl carbon pentaosmium cluster. 15 carbonyl pentaosmium carbon cluster. 15 carbonyl carbon pentaosmium cluster. Here again one more thing we have to add, the total electron count. What we said, that total electron count is number of metal atoms into valency of metal atom plus number of ligands into ligand donated electrons plus or minus oxidation state plus number of heteroatoms into valency of heteroatoms. Right. One more time I will write same total electron count formula here. Right. So when we have one of the metal clusters, initially we will going to calculate total electron count. To define the structure of 15 carbonyl carbon pentaosmium cluster, we will be going to calculate total electron count. Initially, the total electron count is equal to number of metal atoms into valency of metal atom plus number of ligands into ligand donated electrons plus number of heteroatoms into valency of heteroatoms plus or minus oxidation state. This would be the formula for total electron count. Right. So coming to the example, number of metal atoms. Here number of metal atoms are 5. Right. And valency of metal atom. Osmium is counts for the iron group, where it will have D6s2 electronic configuration. So in valency it will have 8 electrons. And number of ligands, here it has carbonyls of 15, so 15 ligands, and electron donated by ligands, that is 2 electrons. Right. Each carbonyl donates 2 electrons. Right. And number of heteroatoms, that equal to 1, that is carbon. And valency of heteroatom, we know that carbon valency is 4. Right. And oxidation state, here in coordination sphere it has the oxidation state of 0. So now total electron count will be equal to 5 into 8 plus number of ligands 15 into number of ligand donated electrons 2 plus number of heteroatoms is 1 into valency of heteroatom 4 plus or minus oxidation state 0. So it equal to 5 into 8 40 plus 15 into 2 30 plus 1 into 4 4. It equal to 74 electrons. 74 electrons, right? The total electron count will be 74, right? Now we have to calculate non-skeletal electrons. Non-skeletal electrons, that equal to 12 into n, where n is equal to what? Number of building block units, or we can say that number of metal atoms. Number of metal atoms or metal ions, right? Here number of metal atoms are 5. So therefore non-skeletal electrons is equal to 12 into 5. That means it equal to 60. 12 5 is 60, right? Therefore, as per total electron count is equal to non-skeletal electrons plus skeletal electrons, then that means 74 is equal to 60 plus 2 into n plus 1. 60 plus 2 into n plus 1, where 2 into n plus 1, summarizing this, 2 into n plus 1 is equal to 74 minus 60. The additional product of 60, when we go for next side of equation, it will become subtract. It subtracts the 74. It equal to 14. So now n plus 1 equal to 14 by 2. When multiple product of 2, when it go from left to right, then it will be divides. 14 will be divided by 2. That equal to 7. So n plus 1 is equal to 7 means n equal to 7 minus 1. That equal to 6. That equal to 6. So as n is equal to 6, the polyhedron will be octahedral, isn't it? Octahedral. So like that, the polyhedron will be octahedral. Here the octahedral, as per Wet's rule, the octahedral may be 3 types. It has 3 types of structures, saying that closo, Nido, Arachno. And thus closo, Nido, Arachno will be defined like this, right? Will be defined in 3 cases. In case 1, when the skeletal electrons equal to that is 2 into n plus 1 equal to 2 into capital N plus 2, 2 into number of metals plus 2, then the structure will be closo polyhedron. Closo polyhedron, when skeletal electrons equal to 2 into number of metals plus 2, right? In case 2, when the skeletal electrons equal to 2 into n plus 1 equal to 2 into n plus 4, 2 into number of metal atoms plus 4, then the structure will be then the structure will be Nido polyhedron. Nido polyhedron. Like that, there will be 4 cases. Case number 3. Case number 3, skeletal electrons. If skeletal electrons 2 into n plus 1 is equal to 2 into number of metal atoms plus 6. Therefore, structure will be Arachno polyhedron. Arachno polyhedron. In case 4, if the skeletal electrons 2 into n plus 1 is equal to 2 into number of metals plus 8, therefore the structure will be hydro polyhedron. Like that, there are 4 different structures is proposed by the Werd's rule or Werd's theory, or we can say that poly-skeletal electron pair theory. So what it means by closure, what it means by Nido, what it means by Arachno, what it means by hydro means, right? Closure, when we see look into the closure, 2 into n plus 1 is equal to 2 into number of metals plus 2, where 2 into small n reflecting the number of vertices, where small n reflecting the vertices number and capital N reflects the number of metal atoms. Correct. So these cases when it comes to closure structure, when it see 2 into vertices number plus 1 is equal to 2 into metal number plus 2, where when we multiply 2 into n plus 1, it will be 2 into n plus 2, right? 2 into small n plus 2, it equal to 2 into capital plus 2, where 2 when get cancelled, we will be get separated one to other, and thus multiplying 2 also will get cancelled. They are equal to small n equal to capital N. So in closure structure, the small n equal to capital N, which means the vertices will be, all the vertices will be occupied by the metal ions, where it comes to a Nido structure. The Nido structure, when it elucidate the equation, it will be summarize the equation. It will be equal to small n vertices number equal to n plus capital N plus 1, where nothing but vertices will be equal to metal atom plus 1. So where it's saying that the vertices will be have one empty with number of one less number with vertices number will be one more than the metal number, which means the structure, the polyhedron structure will be misses one of the metal ion, one of the metal will be missed from the polyhedron, right? The building block unit 1 will be missed from the polyhedron, that reflecting the Nido, isn't it? Vertices number, when it is excess than the metal number, metals will be saying that one short. Vertices number is one more than the metal number, or one metal number will be one shorter than the vertices number, which means one of the metal will be missed from the polyhedral structure, right? Like that. So like that same, when it come to Arachno, n, what is this number will be equal to capital N plus 2, will be capital N plus 2, which means there are two metals will missing from the polyhedron. When it comes to an hydrostructure, it says that the vertices number will be equal to metal number plus 3, which means 3 metals will missing from the polyhedral structure, right? Polyhedral structure, like that the 4 types of different structures will be have in the high nuclear metal carbonyl clusters, right? So when we adapt this particular phenomena for the first example what we are discussed, right? That is what we have discussed, the pentacarbonyl carbon, sorry, 15 carbonyl carbon pentaosmium cluster. It has, right, it has 2 into n plus 1 is equal to 2 into what is this number what we have calculated, the vertices number we calculated as 6. So 2 into 6 plus 1 it equal to 2 into 7 it equal to 14. The skeletal electrons will be equal to 14. And whereas 2 into 2n plus 2 if you want to calculate, that equal to 2 into number of metal atoms, which nothing but it has 5 number of osmium metals. It has 5 osmium metals. So 2 into 5 plus 2, which equal to 2 into 5 will be 10 plus 2 it will be equal to 12 electrons. 12, right? So it may not be equal, right? 2 into n plus 1 may not be equal to 2 into capital N plus 2. So which means the structure may not be closed octahedral structure, right? It may, all the metal atoms are not occupying all the vertices. All the vertices are not occupied by the metal atoms, right? So when it comes to the next, right, 2 into capital N plus 4, if you calculate 2 into number of metal atoms are 5 plus 4, which means 2 into 5 will be 10 plus 4 will be equal to 14. Therefore the skeletal electrons 2 into n plus 1 equal to 2 into capital N plus 4. So which means therefore the structure will be Nido octahedral, isn't it? So it means that one of the osmium will missing from the octahedral polyhedron, right? So it would be having the structure like this. Let us draw the structure. Osmium. This is an empty space which is saying that missing, and it bonding, if it is presence, these 4 bonds may form. So where it is what the octahedral, if it is the empty space will occupies, it will be looks as an octahedral, polyhedron octahedral, where one of the side is missing by the osmium, one of the osmium is missing the polyhedron structure. So this reflects the Nido octahedral structure. So as per the example will have the structure of Nido octahedral. So you students can calculate the structure of different complexes Here I will give you some of that. You try to do and give your answer. The final structure you can give in the comments of YouTube, or you can give your answer in the WhatsApp group. Right. I am giving you the examples. Noted this. Dodecacarbonyl carbon tetrairon cluster. Tetrairon cluster with charge of -2. Right. So here I will give you title. Find the structures of following metal clusters. One is this. Second, 16 carbonyl 6 rhodium cluster. 16 carbonyl 6 rhodium cluster you can calculate. And one more example also I will give you. Third one, 18 carbonyl 6 osmium cluster with charge of -2. You calculate these three and give your answer as YouTube comments, or you can give your answers in the WhatsApp group. Right. So here I will stop. By the next class, we are going to have next topic such as capping rule. So we will discuss the capping rule in the next class. Right. Thank you.